Differentiation power series. This example, we're going to differentiate the Taylor series about 0 for the function e to the power negative 2x. The Taylor series about 0 for f of x equals e to the x is in the form of 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. For this case, for the function f of x as a form of e to the negative 2x, we replace the x with the negative 2x quantity. As the summation form of the e to the x, which is the summation of x to the power k over k factorial, k from 0 to infinity. So then for e to the negative 2x, the summation is of the form 1 minus 2 to the x plus 2 to the second x to the second over 2 factorial minus 2 to the third x to the third over 3 factorial plus and so forth. As in the alternating series form, the summation is negative 1 to the power k multiplied by 2 to the k x to the k divided by k factorial. K equals 0 to infinity as e to the negative 2x. In our case, we are going to differentiate the Taylor series. So we're going to find the derivative of e to the negative 2x, which we know that it's going to be negative 2 e to the negative 2x, as we did it, we do it directly. For the Taylor series expansion, and we find the derivative, that means we're going to find the derivative of 1 minus 2x plus 2 squared x squared over 2 factorial and so forth. Or we're going to find the derivative of this summation. As we treat it as a general form. The derivative with respect to x, so the rest of the term that is not involving x will be treated as a constant, which is negative 1 to the power k, 2 to the power k, and k factorial. For the x to the power k, for the derivative, it becomes k multiplied by x to the power k minus 1. With the term k factorial, which is the same as k multiplied by k minus 1 factorial. The k and the k can be reduced. Now we have the summation as a form of the summation negative 1 to the power k, 2 to the power k, multiplied by x to the power k minus 1, divided by the k plus k minus 1 factorial. And k would start from 1 to infinity. Since the first term is just a constant, the derivative will become 0. And this series is used to represent the function negative 2 times e to the negative 2x. Integrating power series. This example, we are going to use a Taylor series to approximate the definite integral. Retain as many terms as needed to ensure the error is less than 10 to the negative fifth. That means correct to 5 decimal places. For the integrand natural log of 1 plus x squared, we're going to replace it using the Taylor series based on the series of the log of 1 plus x, which is in the form of the x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 and so forth. So the natural log of 1 plus x squared is of the form x squared minus x squared or x to the fourth over 2 plus x squared to the third, which is x to the sixth over 3 minus x squared to the fourth, which is x to the eighth over 4, and so forth. And then replace it into the integrand of the problem. So integral from 0 to 0.4, the integrand is x squared minus x to the fourth over 2 plus x to the sixth over 6 over 3, sorry, minus x to the eighth over 4, and so forth with respect to x. Now we are going to integrate term by term. The first term we get x to the third over 3, second term x to the fifth over 10, next one x to the seventh over 21, and then we get next x to the ninth over 36, and so forth, and evaluate from 0 to 0.4. We place the 0.4 into each x. We get 0.4 to the third power over 3 minus 0.4 to the fifth over 10 plus 0.4 to the 7 over 21 minus 0.4 to the 9 over 36, and so forth, subtracted by the value from replacing with the lower limit 0, which turns out to be all 0. Now we have the numbers for each power. Our goal is to get the estimate that gives the error less than 10 to the negative fifth or correct to 5 decimal places. We are going to check the value one term at a time, starting with the first one. The value of 0.4 to the third power over 3 is 0.02133333. Let's keep it 7 decimal places just to make sure we get enough decimal to see the repeating first 5 decimal terms. So we're gonna subtract this number by 0.4 to the fifth over 10. That means we get the estimate from the first 2 terms of the Taylor series expansion. And we'll get 0.0203013. So far, we have the first 2 digits the same. That means correct to 2 decimal places, but it's not enough. Next, we're going to add another term to the already computed number. So add 0.4 to the 7 over 21 to the number 0.02033013 to get 0.02038874. Now we have up to 4 decimal places, but they are the same as the previous sum. Add one more term. After adding or subtracting by 0.4 to the 9th over 36 to the 0.02038874, we get the estimate value as 0.02038801. As we see, the first 5 decimal places are the same, so we stop the computing at this point. Therefore, the integral from 0 to 0.4 of the natural log of 1 plus x squared with respect to x is approximately equal to 0.02038, as it correct to 5 decimal places.